All right, if you have watched the first two videos, you will realize that we're done with the first, second, and the fourth learning objectives. Now we're going to cover the last learning objective, estimating a propagated error using a differential. All right, let's talk about error propagation. And in fact, I'm going to first start with an example here just to see where we're coming from. Let's say like the measured radius of a ball bearing is 0.7 inch, okay, and the measurement is correct within 0.01 inch. So obviously every tool that we use for measurements have some kind of like an error in measurement. So and this is what's happening here. So the measured quantity is 0.7. This is accurate up to plus or minus 0.01 inch. So now we want to estimate the propagated error in the volume of the ball bearing, because you use this measurement to evaluate the volume of this bearing, and since you have an error in the measurement, well, obviously the volume is going to have some error in it. So now we're going to try to estimate that error. So I wanted to start with this example first so that I can talk about this slide. So here, let's say like x representing the measured value of a variable, which is in fact in the example the radius of the ball bearing. And let's say like x plus delta x is the exact value of the radius, which we don't know because we're just using a tool. And let's say like delta x is the error in the measurement. Okay? So in our case, delta x is plus or minus 0.01. Okay? Finally, if the measured value x is used to compute another value, f of x, in our case it's the volume, right? Volume of the ball bearing. So now what does this difference represent? F of x plus delta x minus f of x. So remember, we made an error in the measurement. So now error is propagated because we're trying to evaluate the volume of the ball bearing. So error propagates. So for that reason, the propagated error is the difference between f of x plus delta x and f of x. So this is the measured value. This is the volume evaluated for the measured value of x, so that contains some error. And this is the exact value, okay? So volume with the exact radius. So that difference is going to tell us how the error is propagated. So let's go back to the example here to estimate the propagated error in the volume of the ball bearing. All right, so what do we need for that? Well, first of all, since we're evaluating the volume, we need to know the volume of a ball, which is in fact 4/3 pi times r cubed, and r is the radius of the ball bearing or the sphere, you name it, okay? And then let's see what we can do with that. So the measured radius is 0.7, and we have an error delta r, right, in between negative 0.01 and 0.01. So it's accurate up to, let's say, 0.01. So what else do we have? So we have dv over dr, right, because the function is v, and v is a function of the radius. So we need the first derivative of v to be able to evaluate the differential of v. So we have two quantities again. One is v, the other one is r, and we have the differential v, and we have the differential of r, or delta r, and these two quantities are essentially the same as we discussed earlier. Okay, so the actual change in v is approximated by the differential of v, and we know how to write down the definition of the differential of v, and here we go. So that is the derivative of v with respect to r, for which you can use the power rule for differentiation. So 3 down and subtract 1 from the power, so that takes you all the way to 4 pi r squared, and we multiply it by dr. So let's try to use the value of dr, in this case it's delta r, right, and also the value of r to evaluate dv. So we have 4 pi, r is 0.7, that's the measured radius, we square it, and we multiply it by plus or minus 0.01. Let's see what we get. And here we go. We get The differential of V calculated as plus or minus 0.06158 cubic inch. So what that means is if you make an error in the measurement up to 0.01, and if you use that measurement to evaluate another quantity, like in this case volume, right, you make this much of error, and as you see that this error is propagated through this calculation. If you use the volume calculation to evaluate the cost of the ball bearing, that means that error is going to be propagating as well. So you can see how important to know how much error you make, or how the error is propagated through calculation of different quantities. All right, it's practice time. Please open the recitation notes, and we have really cool examples gone through step by step in the video. So the first example is going to be about the very first learning objective that we learned. So comparing delta y and dy for the function y equals x to the fourth plus 7, and the point of consideration is -2, and we have delta x to be given to you 0.01, and we're going to evaluate dy and delta y to see what the difference looks like. And in the second example, which is a very cool application example, so you have the total stopping distance of a vehicle provided to you as a quadratic function of x, and x is your speed in miles per hour. So the question is like how your stopping distance changes if you change your speed from 25 to 26 miles per hour. So even 1 mile per hour change may change your stopping distance substantially, and that's exactly what we're going to talk about in that video. Please check that. I have cool pictures over there. Please go through that by yourself. In the next example, we're finding a differential for different types of functions. We're using all the rules of differentiation. So please check this also. This is a good practice. And eventually we have an example similar to what we have gone through in the second video. We're trying to approximate the value cubic root of 26 by using the differential concept. All right, please go through those videos and watch all of them to see what or how I go through those questions with my step-by-step approach. All right, we're done with all the learning objectives of this section. And if you have any questions or comments, please put them down in the comment box below. I'll see you in another video. Bye.